So let's now continue on with the third term of the subsequence. So now what I'm going to do is I'm going to take the interval L minus a third to L plus a third, the interval of radius a third around L. And again, because the sequence of supremums converges to L, I can find you a term in this sequence such that it and all the terms beyond it are inside this interval around L. And now I want you to pick n3 such that 1, it's inside this interval, and 2, such that it is strictly greater than n2. And the reason I'm doing that is the same reasoning as I had here. It's so that when I find a term that is inside here from the original sequence, I am guaranteed that it is beyond this term in the original sequence, so that my things that are in the subsequence, my entries in the subsequence, are in the correct order. And then how I pick my term of the sequence is the same argument. So again, I know that Sn3 is on this side of L because I know it's a monotonically decreasing sequence down to L, so the smallest it can be is L itself. And then what I consider is Sn3 minus a third, which I know at the very least is going to be this lower bound of the interval here, L minus a third, but more likely is going to be to the right of this, inside here. And now, because of the definition of this as the supremum of the set of all terms of the sequence from An3 onwards, I know that Sn3 minus a third is not an upper bound for that set, so there must be something inside that set that is strictly greater than it, and I know that it's everything inside the set is going to be less than or equal to this because it's an upper bound. Therefore I can find a term that is in the correct position here and is therefore guaranteed to be inside this interval around L of radius a third, and I'll pick that as my third term in the subsequence here. And again, I'm guaranteed that it will be further along in the original sequence than this one because of the fact that it's been chosen from a set of terms in the sequence that are all beyond that because I've got this here. And then this continues on. For the fourth one, I'll have an interval of radius a quarter around L. For the fifth one, I'll have a radius of a fifth around L. And you go on making the radius smaller and smaller as you go along. And you can always do this, getting these terms from the original sequence, and they're going to be in the correct order as long as you each time insist that the supremum that you use here not only is inside the interval, but is also greater than this term that was last in your subsequence from the original sequence. So in this way then, I can build a subsequence of the original sequence, and hopefully you'll agree that this subsequence must be converging to L because of the way that I've built it, where each of the terms has had to be in these progressively smaller and smaller intervals around L. So the terms of this sequence are getting indefinitely close to the value L, but they're also staying indefinitely close to the value L because everything subsequent to each term has to be even closer to L than was the requirement for the term before it. So everything is getting and staying indefinitely close to the value L, and hence this must be converging to the value L. So I've found you a subsequence of the original sequence that is converging to the value L. So I've shown then that if you have a sequence where the limit superior exists, that the limit superior is a limit point for the original sequence, as I've got this subsequence that converges to it. What I now want to do is show that it is the biggest of them, and I'm going to do that by contradiction. I'm going to suppose that there exists a subsequence of our sequence that converges to something greater than L, and I'm going to derive a contradiction from that, and hence it cannot have been the case that that thing existed. So let's suppose then that I have a subsequence of my original sequence, and I'll denote this subsequence A, n of k. So again, k denotes the term in the subsequence, and then I've got this function n of k, and it takes in the value k and spits out the value of the term from the original sequence that is in that position in the subsequence. So I've got my subsequence here, and we're supposing it converges to a value which I'll call L tilde. And we're supposing that L tilde is strictly greater than the value L. We're supposing this for the sake of contradiction, where L is the value of the limit superior of my sequence. So we've assumed I have this sequence and the limit superior exists and the value is L, and now I'm assuming that for the sake of contradiction, that this subsequence exists that converges to this value L tilde such that L tilde is strictly greater than L. On the picture of the real line here, you've got L here and L tilde here. And what I'm now going to do is take the distance between L tilde and L, which is here, and divide that by half, so half of that distance, and I'm going to make that equal to epsilon. I'm going to use that as an epsilon. I'm going to now imagine drawing epsilon intervals around these two, and because I know the sequence of supremums converges to this, and this subsequence converges to this, I can use that to derive a contradiction. So I've drawn these intervals on here. So here is the L minus epsilon to L plus epsilon interval around L, and here is the L tilde minus epsilon to L tilde plus epsilon interval around L tilde. Now, because the sequence of supremums converges to L, I know that I can use this epsilon in my definition of convergence, and I can say that there will exist some term in that sequence which I'll call S big N, and obviously it's not the same S big N as we used previously, I'm just using the same notation for it, but there is a supremum in that sequence of supremums such that it and all terms beyond it are inside this epsilon interval around L. Now, I don't actually, for the sake of this proof, even need it to be the case that for all terms beyond it, they are inside here. I just need one of them. So I just need that I can find you this one, S big N, that is inside that epsilon interval around L. And of course, I've drawn it above here on the picture because I know that these are a monotonically decreasing sequence coming down to the value L, so I know it's not going to be on that side. Now, let's apply the definition of this subsequence converging to L tilde. So it converging to L tilde means that, again, I can use this epsilon in my definition of convergence, and I can say that there exists a term in this subsequence which I'll call N, AN, and then it's big K here, so the big Kth term in my subsequence, such that it and all terms beyond it are inside this epsilon interval around L. And this time I do need the fact that it and all terms beyond it are inside there. So it's not just enough for it to be inside there. I want in my for my contradiction, I'm going to need that it and all the terms beyond it are inside that interval around L. And of course I've drawn it here, but it might have been on this side. It's got, you know, I know nothing about where it is. I know this one has to be on this side of the limit, but I don't know anything about where this one is with respect to its limit, whether it's on the right or the left. I've just drawn it on the right, just for the sake of the picture. So I've altered my picture here. So here is my term AN big K, and then this is supposed to show the rest of the tail of the subsequence. AN big K plus 1, AN big K plus 2, etc. All that tail end of the subsequence, it's going to be inside this epsilon interval around L tilde. And the problem here, where the contradiction arises, is that you can see that everything that's going to be inside this epsilon interval around L tilde is going to be strictly greater than S big N, which has to be inside this epsilon interval around L. So everything in this tail end of this subsequence is strictly greater than this value here, which is supposed to be a supremum of something. So this is how we're going to get a contradiction. So I've written down the definition of Sn here, so it's the supremum of the set of all terms of the sequence from An onwards, so the supremum of this set, An plus 1, An plus 2, etc. And of course, it being the supremum means that it is greater than or equal to everything that is inside this set. So here's where the contradiction comes, that loads of the things inside this tail end of this sequence are going to be inside this set, and therefore are going to have to be less than or equal to this value, but I also know that they're strictly greater than that value, and that's the contradiction. So why is it the case that things in the tail end of this subsequence have to be inside here? Well, it's because this goes on forever, and therefore eventually the terms from the original sequence that you've got in this tail end of this subsequence must be inside here. After all, this set contains every element of the sequence apart from the first finitely many n-1 terms. They've been excluded. So this is an infinite tail here. So it must contain bits from this portion of the sequence, because the only bits that were prior to it that have been excluded, there's only finitely many of those. So you can't suddenly build an infinite tail of a subsequence out of the finitely many that have been excluded. So some of the things, indeed most of the things, a lot of the things in this tail end are going to be inside here. And just to make it even more clear, some of the first terms of this tail end, they might not necessarily be in here. Some of them might be small enough, say n of big K here, this value, whatever it is, it might be less than big N, and therefore it might be in the part of the sequence that isn't inside this set. So it's okay. It might be the case also for this next one that it's in this part of the sequence that has been got rid of and isn't inside this set here, but eventually you must get inside this portion of the sequence because only finitely many of the terms ahead of it have been excluded. So eventually you must get to a point in this tail end of the subsequence where it and all the things then beyond it are in this tail end of the original sequence, and therefore you can conclude that they must be less than or equal to this value, but I've also got that they are strictly greater than that value, and therefore there's the contradiction. Ergo, if you have a sequence which has a limit superior, it cannot be the case that there exists a subsequence of that sequence that converges to some value that is strictly greater than the limit superior, i.e. there can be no limit point that is strictly greater than the limit superior. So what we've done is we've shown that the limit superior is a limit point of the sequence and that there is no limit point that is strictly greater than it. Therefore, it is the maximum of the limit points of the sequence when it exists.